This lesson is over logarithmic function properties. We're going to learn about the product rule, the quotient rule, and the power rule. The product rule says if you have log base a of m times n, that is the same thing as log base a of m plus log base a of n. In other words, product multiplication can be rewritten in terms of addition. The quotient rule states log base a of m over n is the same thing as log base a of m minus log base a of n. Again, that means if you have the quotient, means division, can be rewritten in terms of subtraction. The power rule states if you have log base a of m raised to a power of p, can be rewritten as p times log base a of m. The power becomes the coefficient. Example 1, express in terms of sum and difference. In other words, we need to expand the problem. For a, we have log base a of x to the third y squared z. Now notice, log base a of something, there's a collection. So look inside those parentheses. What's happening? Well, since they are multiplying, that means we will apply the product rule. How many values are multiplying? 3. Which means we can expand it. Instead of multiplication, we now use addition, and we will have 3 terms. It will remain log base a, x to the third, plus log base a of y squared, plus log base a of z. Now that we have separated it into individual terms, now we apply the power rule. Log base a of x to the third has a power of 3, so using the power rule, the exponent now comes to the front, and we read it as 3 log base a of x. Look at the second term. Does it have an exponent? Yes. That power now relocates to the front to give you 2 log base a of y. And the last term, does it have an exponent? No. So it will remain log base a of z. This is your expression. 3 log base a of x plus 2 log base a of y plus log base a of z. For b, we have the natural log of the cube root of 5x to the 5th. Now, this one's written a little differently because we don't see an exponent. Instead, we're staring at a radical. So you need to remember your exponent rules. A radical can be written in terms of a fractional exponent. So we have the natural log, and all of that that's under the radical is the 5x to the 5th, but instead of a cube root, the exponent form would be 1/3. So now we have the natural log of something raised to a power. We're now going to apply some exponent rules. Since we have an exponent of 1/3 on the outside, that exponent goes to every factor on the inside, which means it goes to the 5, which would give you natural log of 5 raised to the 1/3, and it also goes to the x. But notice, x already has an exponent. So we must apply another rule, the power to a power rule. If you have a value that has a power raised to another power, you will multiply those exponents. And so 5 times 1/3 would give you x raised to the 5/3 power. Now, looking inside the parentheses, what's happening between these two factors? Since they are multiplying, that means now we can apply the product rule. Product rule states instead of multiplication, you can rewrite in terms of addition. So now it's natural log of 5 to the 1/3 power plus natural log of x to the 5/3 power. So we had two values multiplying. Now we have two separate terms. Since the terms are separated, now we can apply the power rule. The first term does have a power or exponent of 1/3 that now gets relocated to the front, giving you 1/3 natural log of 5. The second term also has a power of 5/3. It gets relocated to the front as the coefficient, and so now you have 5/3 natural log of x. This is the result of your expression. 1/3 natural log of 5 plus 5/3 natural log of x. Example C, we have log base b of m to the 4th over a squared c. Now notice that's log base b of something. I've included parentheses. Now look inside the parentheses. What is the big operation that's going on? Well, it appears to be division, which means we will apply the quotient rule. Now the order of the quotient rule is important. The numerator must be listed first, the denominator will be listed second. So we write it as log base b of m to the 4th minus log base b of a squared c. Pay close attention that I used parentheses for both the numerator and denominator values. That is important. Now, since I included these grouping symbols, these parentheses, we need to look inside the parentheses. In the first set of parentheses, is there any multiplication or division? No. Look in the second set of parentheses. Is there any multiplication or division? Yes. A squared c is multiplication, which means we must apply the product rule inside the parentheses. The product rule states instead of multiplication, I can rewrite it in terms of addition, which would be rewritten as log base b of a squared plus log base b of c. So now that we've taken care of inside the grouping symbols, now we want to see if we can apply any power rules. Do we have any exponents? Yes. The first term of log base b of m to the 4th, now the exponent relocates to the front, giving us 4 log base b of m. Now inside the parentheses, we have log base b of a squared. Notice it has a power of 2. That 2 relocates to the front, now giving us 2 log base b of a. And then plus log base b of c, that has no exponent, so that will remain the same. So we have applied the quotient rule, the product rule, the power rule. Are we done with this problem? No. Notice we have parentheses. We have to look in front to see if there's anything that would cause any changes. In other words, we do need to distribute that minus or the opposite of, which gives us 4 log base b of m minus 2 log base b of a minus log base b of c. That is your expression. For D, we have log of square root of 2 over x. This is your try it problem. First, you should have rewritten the square root as a fractional exponent, then applied that exponent to both the numerator and denominator values. From there, because it was a fraction, we would apply the quotient rule, and then after the quotient rule, apply the power rule, and hopefully you found it to be 1/2 log of 2 minus 1/2 log of x. Example 2, write as a single logarithm and simplify. In other words, it only wants to see the word log written one time. For a, we have log base a of 75 plus log base a of 2. In the lower right-hand corner of the screen, you will see the steps. First, we look for coefficients. If we have coefficients, it means we apply the power rule in reverse. So for A, do we have any coefficients? Any numbers in front of the word log? No, which means we are not going to apply the power rule. Step 2 says look between the logs to see if you have an addition or a subtraction. For A, since we have addition, well, if we do that in reverse, the addition means we will apply the product rule. So we keep the same log base A, and the values 75 times 2 are now written in terms of multiplication. Now 75 times 2, can we really multiply that? Absolutely. So it would become log base A of 150. That would be your single logarithm. For B, we have 1/2 log A minus log 2. So again, according to the steps, we look for any coefficients. Do we have any coefficients? Yes. We have that 1/2 in front of the log A, so we will apply the power rule. We rewrite it to be log of A raised to the power of 1/2 minus log 2. Now log 2 has a minus sign in front, but it has no number, so that's why it will remain the same. We've taken care of the power rule. Now we look for what's happening between the logs. Because we see subtraction, that means we will apply the quotient rule. The quotient rule means division, and order is very important. Whatever's listed first goes in the numerator. Whatever's listed second goes in the denominator. So we now have it written as a single log, but the problem is I don't want to keep the 1/2 as a fraction. Instead, what does that really mean? Well, it means a radical is involved. So instead of A to the 1/2, I would now write that as log of square root of A all over 2. For C, I have log of the value x squared minus 5x minus 14 minus log of x squared minus 4. So first, do you have any coefficients? No. So next we look between the logs. Notice I have log of something minus log of something. Because it's a minus or subtraction, we will apply the quotient rule. So again, order is very important. Whatever's mentioned first will be in the numerator, which is x squared minus 5x minus 14. Whatever's mentioned second will be in the denominator, which is x squared minus 4. So we now have a single log. It's log of a fraction. And we know anytime you have a fraction, you want to reduce. But we can only reduce when things are written in factored form. So we will need to factor the numerator. So take the time now to do that. Hopefully you found x plus 2 times x minus 7. And we need to factor the denominator. Take the time now to do that. Hopefully you found x plus 2 and x minus 2. So we now have it factored, but now we want to see, can this reduce? Is there anything that appears in the top and in the bottom? Yes. The x plus 2's will reduce, leaving you log of x minus 7 all over x minus 2. For D, we have the natural log of x minus 4, bracket, natural log of x minus 4 plus natural log of x plus 4, close bracket. In this case, we have grouping symbols, so we want to focus our energy inside the brackets. And inside you see natural log of something plus natural log of something. Because you have addition, that means we will apply the product rule. So we can rewrite that as multiplication. So natural log of x minus 4 times x plus 4. Since they're timesing or multiplying, can you actually multiply those two values? Yes. So take the time now to multiply x minus 4 times x plus 4. Hopefully you found the result to be x squared minus 16. So we've taken care of what's inside the grouping symbols. Now we look at the problem as a whole. Do we have any coefficients? Yes, we have a 4, so we will apply the power rule. It'll now be natural log of x minus natural log of x squared minus 16 raised to the power of 4. So now that we've taken care of the power rule, we now look between the logs. Since we have natural log of x minus the natural log of something, we will apply the quotient rule. Again, order is very important. So the result would be natural log of x all over the value x squared minus 16 raised to the 4th power. Now we're going to talk about a new rule called log of a base to a power. And it states if you have log base a of a to the x power, that will equal x. Well, if you go back to the definition of logs, that really means a to some power equals the result of a to the x. What would be that power? Well, that would be x. So to better understand this, let's look at an example. Example 3 states to simplify. For a, we have log of 10 raised to the negative k power. Now in this example, do you see a base or a sunken down number? No. So if you do not see a base, what is the understood base to be? Well, there's an imaginary 10 there. So if I were to change this from log notation to exponent notation, what that means is my base, 10, raised to some power gives me 10 to the negative k power. What would be that exponent? Well, that must be negative k. For b, we have log base 7 of 7 to the 3rd power. Again, to really understand this, let's rewrite this as an exponent. My base, or sunken down number, raised to some power gives me 7 to the 3rd power. What would be that power? Well, that would be 3. For c, we have the natural log of e raised to the 8t power. In this case, do you see a base or a sunken down number? No. Now, since you see ln, that means natural log, by default, it runs off of what base? Well, that is the base e. So to understand this, let's rewrite this as an exponent. E raised to some power gives me e raised to the power of 8t. What is that power? Well, that would be 8t.